In this video, we're going to talk through some of the curved arrow mechanisms that are important to carbohydrates. We'll start with the interconversion between the cyclic and acyclic form of monosaccharides. Let's use glucose as the example. This structure shows the cyclic form of glucose. Notice its ring shape. Glucose is considered a heterocycle because the oxygen atom is ring. This method of drawing carbohydrate structures is known as a Haworth projection. The bolded bonds at the bottom show perspective, indicating that these atoms are closer while the others are further away. The actual three-dimensional structure is buckled into a chair or boat conformation like cyclohexane. This structure shows the acyclic form of glucose. Notice that the ether functional group was converted to an aldehyde. This method of drawing monosaccharides in a straight vertical line is known as a Fischer projection. Since it can be used to clearly show the stereochemistry or arrangement around each chiral center, it is commonly used by biochemists when discussing carbohydrate structures. To show the cyclization of a straight chain glucose, we can draw the acyclic form with its tail wrapped around. I have omitted some hydrogens here for clarity. In this arrangement, it is easier to see how the formation of a bond between this carbon and this oxygen will give the cyclic glucose form. Let's actually use the bond line version of this structure for our mechanism. The extra electrons in the double bond, a nucleophile, are used to grab the hydrogen from the other end of the chain. The bond between that hydrogen and this oxygen is broken. The resulting nucleophilic oxygen attacks the electrophilic carbon on the other end of the chain. This gives us the cyclic form. This type of mechanism is sometimes called ring closure for obvious reasons. The ring opening mechanism is similar but reversed. The ether bond is broken, forming a nucleophilic oxygen. This oxygen grabs a hydrogen while its bond is transferred to the oxygen. And the extra electrons go to form a double bond. This gives us the acyclic form. Now let's discuss the curved arrow mechanism for the formation of a glycosidic bond between two monosaccharides to form a disaccharide. We'll use the formation of maltose, a 1,4-disaccharide of glucose, from two individual glucose molecules. This is an example of a condensation reaction where a water molecule is lost. The 1,4 designation tells us where the glycosidic bond will be located, and therefore which atoms from the glucose are involved. In this case, the 1 carbon, the anomeric carbon, on this molecule will link via an ether group to the number 4 carbon on this molecule. The hydroxyl group is lost from one molecule, grabbing the hydrogen from the other. The hydrogen-oxygen bond is broken, leaving a negative oxygen. The negative oxygen nucleophile attacks the positive carbon electrophile on the other molecule. That gives us the disaccharide maltose, which contains a 1,4 glycosidic linkage. Now let's look at the reverse process, the hydrolysis of the glycosidic bond. Considering the maltose molecule again, we see that the mechanism is essentially a reverse process of the previous example, and a molecule of water is incorporated. The glycosidic bond breaks, forming a bond with water's hydrogen. The bond in water is broken, leaving a hydroxyl nucleophile to attack the electrophilic carbon that's resulted from the glycosidic bond breakage. That gives us 2 molecules of glucose. In these examples, we used the common monosaccharide glucose, but you can apply the same methods when considering reactions involving any mono and oligosaccharides.